Awesome. Thanks very much, Paul. So first and foremost, thanks for having me. I must confess, I'm definitely not an expert in Ricci Flow, but nevertheless, I'm hoping to share with you some cool aspects of Ricci Flow that I enjoy at least. So the aim of this lecture, and I guess I'm not sure, but I suspect I'll be asked to do the one next week as well. The aim of these talks.
Yes, please.
I say yep. So the aim is to sort of give a gentle introduction to ancient Ricci flows, at least for the uninitiated, perhaps. But the main goal that I want to get out of this talk, at least, is to sort of provide a more modern treatment of the classification of some special examples of ancient Ricci flows, specifically the shrinking gradient Richie Solitons. This classification was actually quite instrumental to Perelman when he proved the Poincaré conjecture. But since that proof was done, there have been some cool new techniques that have come out that perhaps give a simpler classification of these guys, simpler than the classification that Perelman used, at least. So to make a start, Ricci flow. We've been talking about, I think we've been talking about the Hughes equation and the mean curvature flow so far. The Ricci flow, of course, is defined analogously. If you've got a Riemannian manifold with a Riemannian metric, then a Ricci flow that starts from that metric is simply a one-parameter family of smooth Riemannian metrics on this same manifold, so that the time derivative of the Riemannian metric happens to coincide with -2 times the Ricci curvature. Now, the minus sign is quite important, because the fact that the minus sign is there means that this does actually behave like the Hughes equation instead of the backwards heat equation. So at the very least, studying ancient Ricci flows is akin to studying ancient solutions to the heat equation. The -2 there, slight technicality. It doesn't really matter if there's a 2 there or not. It makes some of the formulas a bit easier. All right, so this is what a Ricci flow is. This is a PDE, of course, because the Ricci curvature is a second order nonlinear and non-elliptic partial differential operator. So this is a PDE like the Hughes equation, except it's not strictly parabolic. Short time existence can be achieved by using the so-called de Turck trick to sort of quotient out by this non-elliptic part. All right, so I'm going to be doing a lot of shameless stealing of other people's pictures. This is what the Ricci flow does according to the picture on Wikipedia. So the idea, roughly speaking, it's kind of akin to what you might expect for the mean curvature flow. Regions with positive curvature, so these kinds of regions here, they shrink under the Ricci flow, whereas regions of negative curvature, like sort of these guys in here, they tend to expand a bit under the Ricci flow. If you try and work out what happens all together, you keep shrinking the positively curved bits and expanding the negatively curved bits. It's interesting to see how these phenomena compete with each other and what the end result is. So according to this picture, eventually when we get down to here, the curvature looks like it's positive everywhere, or at least non-negative everywhere. So it looks like the positive curvature has won in the end. And ultimately, the behavior we expect is that this manifold will shrink under the Ricci flow. Now, before we get too far into the details here, there's something that I feel needs to be pointed out, since we have just spent a bit of time talking about the mean curvature flow. In the mean curvature flow, it makes sense to look at, well, the special one-dimensional example, which is curve shortening flow. And so we had lots of interesting examples about ancient solutions of the curve shortening flow. What I think is quite incredible about the curve shortening flow is sort of given by this picture here. which was ripped out of Klaus Ecker's book on the mean curvature flow. The idea is that, well, if we've got this one-dimensional manifold here, which is this spiral-looking thing, if you apply curve shortening flows to that, you would expect that, well, because you can trap this curve with this circle out here, that sort of the curve is going to shrink. But also we might wonder whether the first singularity that occurs with this curve shortening flow, whether it occurs before it actually collapses to the point, i.e. is it true that this curve is going to unravel before it hits a single point? And one of the interesting results in the theory of mean curvature flow is that this unraveling of the spiral does in fact happen quicker than the shrinking. So that's all well and good, but at least in terms of a picture like this, there's no easy picture you can draw for one-dimensional Ricci flow, at least nothing that gives you any value, because unlike the mean curvature flow, the Ricci flow is an intrinsic flow. The Ricci curvature is intrinsic. It doesn't care where the manifold is embedded. Now, Ricci curvature is essentially, well, it's a contraction of the Riemann curvature, which is a measure essentially of how derivatives commute. If your manifold is one-dimensional, then of course everything commutes. There is no Riemann curvature, there is no Ricci curvature. And so even though we get this fun behavior occurring for the mean curvature flow, the Ricci flow doesn't actually change this curve at all, because there's only one closed one-dimensional manifold, that's the circle. And the only geometric quantities that you can use to distinguish your circles are essentially how long they are. So Ricci flow is not an interesting thing to study in 1D. However, you know, if we jump up a dimension, maybe there's some hope we'll get some interesting behavior. So in two-dimensional Ricci flow, what allows us to get a lot of good results is the observation that the Ricci curvature of a Riemannian metric is always in the same conformal class as that Riemannian metric. So what that means is that the Ricci flow actually preserves conformal class. So if you've got a solution, to the Ricci flow, then it must look like some scalar function multiplied by some Riemannian metric. So you may as well assume that Riemannian metric is just your initial Riemannian metric. So therefore we would expect that the Ricci flow should just simplify into a scalar PDE for this scalar function u, whose inputs are the time parameter as well as the manifold itself. And indeed that is the case. We have this equation 1 here that says that the time derivative of this scalar function u should be the same as the Laplacian of the logarithm of u, the Laplacian taken with respect to your G0 metric, and then you subtract the scalar curvature of that same G0 metric. So I'm not going to spend too much time talking about this, at least not in this talk. Maybe we'll get to it a bit more next week. But I wanted, before we move on perhaps to higher dimensional Ricci flow, you know, maybe a picture is in order here. So this picture, it was taken from Peter Topping's notes on the Ricci flow. So I've got a picture here. Topologically, this manifold is just the two-sphere. You can see it's got sort of S1 fibers here. Now, in 2 dimensions, the Ricci curvature, the Riemann curvature, and the scalar curvature are all essentially the same thing. And they're basically the same as the Gaussian curvature. And so again, like we saw before, in areas where the Gaussian curvature is positive, we expect some shrinking to occur. In areas where the Gaussian curvature is negative, we would expect expansion to occur. All right, now let's get on with the actual topic for this seminar series: ancient solutions to these equations. So as we would expect, like what we saw for the mean curvature flow and the heat equation, we call a solution to the Ricci flow, we call that solution ancient if it exists on a time interval that goes all the way to minus infinity. So for various reasons, we might actually be interested in finding out what ancient Ricci flows actually look like. Now, I'm going to try and make a move towards sort of classifying what these things look like. But to start, the very first thing we need to do is look at the evolution of the scalar curvature under the Ricci flow. So hopefully this will become clear shortly why we care about this. So a computation that can be done and is done in various books is that if you've got a Ricci flow, the scalar curvature of your Riemannian metrics, so scalar curvature is just the trace of the Ricci curvature and is therefore a scalar function, that the time derivative of this scalar function is equal to the Laplacian of this scalar curvature, the Laplacian taken with respect to your metric g of t, plus this term here, 2 times the norm of the Ricci curvature squared. And this norm is usually taken with respect to your Riemannian metric as well. One of the first important things that helps us try to classify ancient solutions is the observation that this term is actually always positive. Now, why is that interesting? Well, not only is it positive, but it actually is bounded, sorry, it's not bounded, it bounds your scalar curvature squared times some, I think it might be 1 on n. Shout out if that's wrong. Maybe I got the, the number the wrong way around there. But this Ricci curvature squared term is basically, it controls the scalar curvature squared. Now, the reason this is interesting is because, well, that means that, you know, roughly speaking, maybe we would expect the scalar curvature to sort of behave like the scalar curvature squared. What this means is that if we go backwards, we would expect the scalar curvature to be non-negative, because if it were ever negative somewhere, the backwards behavior of solutions to this ODE would lead us to expect that this actually blows up in finite time, finite backwards time, which would contradict the assumption that this flow is ancient. So this can be made precise in the compact setting very, very easily with the maximum principle. Because if your manifold is compact and your scalar curvature at any point and at any time ever happened to be negative, you would simply take the points that extremizes that negative value of the scalar curvature, run your flow backwards in time, and you would find that you would get blow up in finite time. So this tells us immediately that ancient solutions to the Ricci flow on compact manifolds at least have to have non-negative scalar curvature. Now what's quite remarkable, something that was done in a paper in 2009 after Perelman's work, is that this is actually true without the assumption on the compactness of the manifold. So if you've got a complete ancient solution to the Ricci flow, I think, well, hopefully everyone in this geometric PDE seminar appreciates why it's important to assume that your manifold is complete. If you've got a complete ancient solution to the Ricci flow, then your scalar curvature has to be non-negative. Now, I won't go into the proof of this this time. This perhaps is something I might like to address next week, because I think the proof might be a little on the technical side to lead off with. But nevertheless, this is a very, very important theorem that I will be using a lot in this lecture at least. Now, not only is our scalar curvature greater than or equal to 0, but we can also play this kind of game with the sectional curvature. Because in 3 dimensions at least, the sectional curvatures also obey a nice PDE that lends itself quite nicely to the maximum principle. And Chen did this exact same thing for this sectional curvature as well. If you happen to have a complete and ancient Ricci flow on a 3-dimensional manifold, then it has to have non-negative sectional curvature. As far as I can tell, the proof of this does follow quite, it's akin to the proof of the fact about the scalar curvature. Again, I think this would be a cool thing to go through, but we won't do it now, but I will still be using these results. All right, now perhaps let's make baby steps towards trying to classify all ancient Ricci flows. A very special class of solutions to the ancient Ricci flow equation are Richie Solitons. You can think of these as sort of traveling wave solutions of the Ricci flow. So in particular, what that means is that the structure of Richie Solitons is determined completely, the structure of Richie Solitons under the Ricci flow is determined completely by what it is at initial time. So definition, if you happen to have a smooth and complete Riemannian manifold, you call it a gradient shrinking Ricci Soliton if there happens to be a smooth function f that goes from your manifold into the set of real numbers, so that this almost Einstein equation holds. So if we got rid of the Hessian term here, we just have the Einstein equation, but instead we're going to insist that the Ricci curvature of G plus the Hessian of f taken with respect to your Riemannian metric G is the same as some scalar multiple of G itself. Now, we call this soliton a shrinking soliton if lambda is strictly positive. On the other hand, if lambda equals 0, then we call it a steady Ricci soliton. So how exactly are these traveling wave solutions? Well, again, this is a bit of an annoying computation, but the idea is that if your initial Riemannian metric happens to have this particular form, then its evolution under the Ricci flow is given by some scaling function of time multiplied by a diffeomorphism, a time-varying diffeomorphism applied to your initial Riemannian metric. Now, this scaling function is 1 minus lambda t. This is basically why lambda strictly positive is called the shrinking case. Because if lambda is positive, this sigma function is decreasing as time increases. On the other hand, if lambda equals 0, we call it steady because it's not shrinking or growing. It's only changing by this time-varying diffeomorphism here. So where does this time-varying diffeomorphism come from? Well, it's basically the diffeomorphism generated by a vector field. And in this case, the vector field is the gradient of f taken with respect to G naught. So one of the reasons these become important is because as we approach a generic singularity of the Ricci flow, under some assumptions, we might expect to be able to sort of rescale and zoom in. And the hope maybe is that we get something resembling a gradient shrinking Ricci soliton. Making this precise and showing that it was always true was the subject of a lot of Perelman's work. And as I suggested, this was quite useful in resolving the Poincaré conjecture. Okay, so now let's have a look at the problem of trying to classify gradient shrinking Ricci solitons. All right, well, some examples. Now, don't be fooled. These pictures I've got here are again taken from Ecker's mean curvature textbook. I guess because I couldn't be bothered to find my own examples of these things. But the idea is that the cylinder and spheres are actually examples of gradient shrinking Ricci solitons. So the sphere, of course, well, I mean, the sphere is just an Einstein metric. Ricci curvature does actually equal lambda times G for some lambda strictly positive. And so what that means is that this metric shrinks, the solution being 1 minus lambda t times G naught. Now, the shrinking cylinder, on the other hand, it's a bit more tricky. Basically, the cylinder is going to be a Cartesian product, a direct Riemannian product of flat Euclidean space with a sphere. This has no Ricci curvature, but this does have strictly positive Ricci curvature. So it might be unclear at this stage why this is a shrinking Richie soliton, but hopefully we'll see soon why that is indeed the case. So here are some basic examples of gradient shrinking Richie solitons. All right, so those are some basic examples of shrinking Richie solitons. What about the steady ones? Well, one cool example of a steady Richie soliton was given to us by, I'm pretty sure it was by Hamilton. This is a Riemannian metric on R2. It's not the standard flat Euclidean Riemannian metric on R2. It's the metric given by this quantity here. The standard Euclidean metric scaled according to this sort of parabolic condition here. Now, in order to be, by definition, in order to be a gradient Ricci soliton, there needs to be some smooth function f associated to it, and indeed there is one. But as we'll see as we go through this lecture, knowing what f is precisely is nowhere near as important as knowing what the gradient of f is. Because remember, the gradient of f, which is a vector field, this is the thing that tells us how this soliton evolves under the Ricci flow. It turns out that this vector field is -2 times the sort of radial vector field here. So this vector field is pointing inwards. And this tells us how this soliton evolves under the Ricci flow. The metric is kind of changing, but its structure as a Riemannian manifold doesn't really change. All right, so here's a picture of what this soliton looks like. I'm afraid I didn't cite this, but I picked this up from a Stack Exchange post somewhere. So if you're trying to work out what the actual shape of this metric is, well, it turns out that it's most convenient to study this in polar coordinates, because this Ricci soliton is rotationally invariant. And if you do that, then you get g equals dr squared, r being the radial coordinate, plus tan h squared of r times d theta squared, theta being the angular coordinate. Now, one natural question to ask is, well, can you do this in higher dimensions? And it turns out that you can, but it's much trickier. And the reason for that, well, to explain why it was so easy to construct this particular soliton, notice again that that the fibers in here, they're all copies of S1. And S1 has no intrinsic curvature. And so from that perspective, constructing this simplifies a lot. Trying to do it more generally on Rn, say, where the fibers are now the sphere of dimension n-1, if n is bigger than 2, that now does have lots of intrinsic curvature. So it's more difficult to construct, but this was the content of one of Bryant's papers, basically constructing the analogous Ricci soliton on Rn for higher dimensions. All right, now, the first major tool that we can use in order to classify 3D solitons, especially in the shrinking case, is of course, first, massive contribution to the Ricci flow, which was given to us by Hamilton in 1982. So the theorem says, if you happen to be compact and your initial metric has positive curvature, then if you run this Ricci flow, the solution is going to terminate in finite time. But not just that, it turns out that close to the singular time, provided you renormalize, the metric actually converges in the Gromov-Hausdorff sense to the round sphere, or at least a quotient of the round sphere by a finite subgroup. Now, why is this so helpful? Well, if you have a gradient shrinking Ricci soliton, you also know that it disappears in finite time. And you also know that it converges in the Gromov-Hausdorff sense to basically the same Ricci soliton. And so therefore it can't possibly converge to something different. And so what that means is that if your compact gradient shrinking Ricci soliton happens to have positive curvature, then it must be the sphere up to universal cover. Must be the sphere. So, well, since this is an old result, I won't go through the proof of this. But yes, I'll just reiterate that this in fact shows us that the three-dimensional compact Ricci solitons of positive curvature must be the round sphere or a quotient thereof. All right, so that was the compact case, positive curvature. The bulk of what I want to do today is talk about the non-compact positive curvature case. Because now it's not so obvious why the maximum principle is helpful to us. Now, if we're classifying non-compact gradient shrinking Ricci solitons, it becomes incredibly important to get really good asymptotic information. You might ask, asymptotic information about what? Well, lots of things. The first of these is going to be the potential function itself. So, theorem. Suppose we do have a gradient shrinking Ricci soliton with lambda equals 1. It doesn't cause any loss of generality to assume that lambda equals 1 because we can always scale and change lambda accordingly. All right, we've got a gradient shrinking Ricci soliton, lambda equals 1. What happens to the potential function? Well, it turns out that in this case, there are going to be two constants, let's call them C1 and C2. And there's also going to be a nice reference point, x0, that's in your manifold. So that provided you're far away from this reference point, your potential function is going to have these nice bounds. So, roughly speaking, we would think of this as f of x is basically equal to a quarter of x squared, at least in the Euclidean sense. So roughly speaking, f has a quadratic growth and the coefficient of that quadratic is a quarter. Now, I've written a remark here to explain why this is actually a really good theorem. It's in the sense that this coefficient is optimal. So this is where we turn back and sort of go to our cylindrical example. This remark here explains why the shrinking cylinder is actually a gradient shrinking Ricci soliton, because Rn is a gradient shrinking Ricci soliton. Now, as a novice to Ricci Flow, I think this kind of confused me for a long time, and perhaps it still does. Flat Euclidean space has no Ricci curvature. So it's an Einstein metric, Einstein constant 0. So, it's a steady Ricci soliton. And yet, you can also interpret it as a shrinking gradient Ricci soliton. Why is that? Well, if we remember what our Ricci soliton equation actually was, it was the Ricci curvature plus the Hessian taken with respect to G equals lambda on 2 times G. In the flat Euclidean space, there's no Ricci curvature, but if we choose f of x to be the absolute value of x squared divided by 4, so the absolute value does actually make sense in the Euclidean sense, then when we take the Hessian of this, we actually get the Riemannian metric itself back, the flat Euclidean Riemannian metric. So this means that Rn is a shrinking soliton. And that explains why the cylinder is also a shrinking soliton, because it's the direct product of two separate shrinking solitons. But the other important thing to note here is that this coefficient of a quarter is optimal, because it's exactly what you get in the Gaussian case. Now, saying this now, I realize that optimal perhaps might not be the right word here, because since you've got a quarter which bounds it from above and from below, it's not so much optimal as the sense that we know this is how it actually has to be. But anyway, let's have a look at the proof of this theorem. Lots of good geometry gets fleshed out in the proof of this theorem. All right, upper bound. It turns out that proving that f is controlled by something with quadratic growth is much easier than proving the lower bound. So let's start with the upper bound. First and foremost, an integral. It turns out that if you've got a gradient shrinking Ricci Soliton, again, without loss of generality, assume that lambda is 1, then we actually get an integral. It turns out that the scalar curvature plus the absolute value of the gradient of f squared, keeping in mind, of course, that this all depends on g, that minus the function has to be constant on your entire manifold. Of course, this is assuming that m is connected, but I don't think I've made that assumption yet. All right, we've got this integral. Now, it turns out that not only can we do this, we can also assume that C0 is equal to 0. And we can do that by adding a constant to the function f. Now, you might be wondering, why can we do that? Well, if we go back to our Richie Soliton equation, if you add just a constant to the function f, this Hessian doesn't change. So you've still got a gradient shrinking Richie Soliton. All right, so we can assume that the constant C0 is equal to 0. Why does this help us? Well, remember our heavy hitting theorem from before that says that all ancient complete Ricci flows have non-negative scalar curvature. Of course, a gradient shrinking Richie Soliton is an example of an ancient Ricci flow. So the scalar curvature must be non-negative. So combining this and this, we get this fun estimate here, namely that the gradient of f, taken with respect to g, the square of that is controlled by f. Now, this is basically just, you can interpret this as sort of an ODE. What you do is integrate it out, and you end up with this estimate here. F of x is controlled by a quarter times the distance between x0 and x, plus 2 times the square root of f of x0. Now, I haven't actually told you what x0 is yet. At this part of the proof, x0 can be anything. So for now, just pick any old x0. You do this, and you get your upper bounds taken with respect to x0. Now, the lower bound is much trickier, requires lots of knowledge. Well, we need to know how geodesics operate, essentially, in order to get this lower bound. All right, so at the moment, just pick any 2 points, x0 and y. Again, we haven't set x0 yet. Let's suppose that we've got a minimal geodesic that lies between these 2 points. And let's, without loss of generality, assume that this geodesic is parametrized by arc length. Now remember, we're only interested in proving this estimate for y really far away from x0. So we may as well assume that the length of this geodesic is at least 2. I've seen a few proofs of this result around the place, actually. The one that I'm basing this off is a paper by Müller and Hasselhofer, where they sort of insert a proof of this into the appendix. The subject of this paper was compactness of gradient shrinking Ricci Solitons. So anyway, on with the proof. I'm going to define a function that's meant to be defined along this curve. It's meant to vanish at the start and at the end of this curve. This is essentially a tent function. Starts at 0, goes up, stays at 1, and then goes back down. So I suspect that this proof probably works with lots of choices of sort of functions which vanish at 0, but of course, the proof simplifies dramatically if it's piecewise constant, sorry, piecewise linear. All right, now here's where we've got our geometry really coming into play here. Recall that, well, gamma was chosen to be a minimal geodesic. Since we're assuming that this function is minimal, that means that we get lots of information about the first and second variation formulas. Using these variational formulas, it turns out that by virtue of the fact that this must be a minimal geodesic, we get this estimate here. Now, it turns out that on Riemannian manifolds, where you take variations of geodesics, you get this nice Ricci curvature term popping out here. So this estimate here, just a consequence of variational formulas for minimal geodesics. This equation, on the other hand, well, that's just, you know, literally compute what phi dash is and integrate it, because we know what phi is based on this. It turns out that the integral of phi dash squared from 0 up to s naught is equal to 2. All right, why does that help us? Well, remember, we know what the Ricci curvature is because we're a Ricci soliton. The Ricci soliton, again, just to make this painful for you again by writing out the exact same equation over and over again. The Ricci curvature is the same as the metric minus the Hessian of f. If we simply plug in these vectors into this bilinear form equation here, we find that the Ricci curvature of this direction is equal to 1/2, because remember, lambda is equal, oopsie. Yes, is equal to 1/2 minus, now we're taking the derivative of f with respect to gamma dash twice. Okay, why does that help us? Well, this inequality here is found by basically replacing this Ricci curvature term with this stuff and rearranging. This is exactly what this is here. So that's just a rearranging. What happens next? Well, this is a PDE and analysis talk, so we've got to include some integration by parts somewhere. Take one of these derivatives, put it over here. What you're going to end up with is something like the integral of phi times phi dash times the gradient of f. But remember, the gradient of f was bounded by f. So that fact as well allows us to deduce this final inequality here. So remember that at this stage, x naught and y are arbitrary. It's at this stage, however, that we're actually going to pick our x naught. Based on this estimate, we are now guaranteed that there is an absolute minimum of f. Why is that true? Well, we'll take a minimizing sequence of f. We can't have x naught shooting really, really far away from y, because if it were to do that, then this term would get really, really large. And so this term would also get really, really large, which contradicts the fact that this is a minimizing sequence. So we are now guaranteed an absolute minimum of this potential function f, and we're going to make x naught, we're going to now set x naught to just be that absolute minimum. Okay, we've now got our reference point, and we can now continue the proof to try and show that we've got this lower bound. What comes into play now? Well, lucky me, I managed to find a minimizer of this potential function f. Because everything's nice and smooth, that means that the Laplacian of f, taken with respect to g, must actually be non-negative at the point x naught. So that's just elementary calculus there. All right, why is this an important observation? Well, remember we had that, I guess I'll do it one more time. Ricci curvature plus the Hessian of f equals g on 2. If we take the trace of this equation, trace of the Ricci curvature is the scalar curvature, trace of the Hessian is the Laplacian, and trace of the metric is just n. So if we take the trace of the Richie Soliton equation, we get that the scalar curvature has to be the same as the Laplacian of f. Sorry, has to be the scalar curvature plus the Laplacian of f has to be equal to n divided by 2. Why is this helpful? We know that this term is now greater than or equal to 0. So what that tells us is that at this reference point, the scalar curvature has to, well, we already know it has to be non-negative, but we now also know that it has to be less than or equal to n on 2. Finally, this tells us that the same has to be true for f of x naught, because remember we had that integral that told us how we could find the scalar curvature in terms of the function f and the gradient of the function f. We're at an absolute minimum, so the gradient has to be 0, which means that f of x naught has to be between 0 and n on 2. These bounds on the absolute minimum, these are very, very handy, because what we'll do now is pull back our original estimate. Remember, this is true for all x naught and y, but we've now fixed x naught to be our absolute minimum. Fixed x naught, we're now going to look at what happens when we vary y. Well, this term is now controlled thanks to this. And so we put that on the other side, and what we get is this, that the square root of f of y is greater than or equal to, stuff. But the important thing is that the dominating term is this guy here. So this is actually the proof of the lower bound. Okay, sweet. So that's actually the proof of the upper and lower bounds for the potential function of a Richie Soliton, a gradient shrinking Richie Soliton. In order to make a move towards using this in classifying the gradient shrinking solitons, it turns out that we also sort of need good asymptotic behavior of certain integrals of curvature. So this is a bit of a technical lemma. I'm finding it hard to motivate this to you right now, but I guess the power of this particular theorem comes from the fact that we already know that f of x behaves like distance squared on 4. This lemma tells us that if we integrate the scalar curvature on dr, where dr is the set of x with f of x less than or equal to r squared on 4, then this integral is bounded by n on 2 times the volume of that same set. Now, it might look a bit artificial to use such a set, but the reason this is important is because of this bound. This bound essentially tells us that for really, really large r, d of r is, basically equivalent to the ball of radius r centered at x naught. This is true for large r. So this is why this is handy. The proof of this, I think, is quite cute. So remember, first of all, remember let's just define a function v of r, which keeps track of this term here, the volume of that set. All right, remember that's, so remember we had that the scalar curvature plus the Laplacian of f with respect to g had to be the same as n divided by 2. Basically, we're going to use that and integrate around the set dr. That's all this equation is. Now again, we're using our fun integration by parts. Well, not really integration by parts. We're sort of replacing the integral of the Laplacian of f around a domain with the corresponding integral around the boundary of this domain. Now, what you do then is take the gradient of f and dot product it with the outward pointing normal vector. But because dr was constructed to be the set so that f of x was less than or equal to r squared on 4, we know that the outward pointing normal vector has to be in the same direction as gradient f itself. So this is pretty cool because we're now taking the gradient of f and taking the product with gradient f itself. And so that means, well, of course, that has to be non-negative. There is a slight technicality here because it may be the case that, you know, the gradient of f might actually vanish, but there are technical ways around that that I won't go into now. But why is this helpful? Well, looks like we won't have time to prove this today, but I would like to state this, and I guess I'll get into it next time. The theorem, which was proved by Muntiano and Wang in 2015, if you happen to have a gradient shrinking Ricci soliton, it happens that the sectional curvature is non-negative and the Ricci curvature is positive, then actually you have to be compact. So roughly speaking, the proof goes by assuming that your soliton is non-compact and using this asymptotic behavior of the scalar curvature on balls as well as the growth of the potential function itself to reach some contradictions. So quite excited to go through the proof of that with you, but it looks like I'm afraid it'll have to wait until next time. So I'll leave it there and thanks for your attention.